So today we're going to be talking about soil modelling, soil mapping. I'll use the terms interchangeable. Maybe we'll just go with soil mapping just because it's a bit simpler, a bit more straightforward. We'll talk about, we're going to go through how to set up your farm and FarmLab to do some soil mapping with the FarmLab tools. We'll also talk about some of the best practices when it comes to soil mapping more broadly. There will be a focus on carbon. Most of the maps we'll talk through are going to be carbon, but I will touch on the difference between mapping something like soil carbon and mapping soil nutrients and mapping soil properties, because the way that you'll map these will be different according to what it is you're measuring, only because there are a million and one different things you need to factor into account. We'll try and take 999,000 of those out of the equation for you, but still a few considerations you need to know. And then we'll go through some of the modeling techniques. We'll talk through reading a model, understanding it, and how to know if you've got an accurate model or an inaccurate model, and then I can open to any questions. So please, if you've got any questions along the way, throw them in the Q&A there as well, and we'll get to them right at the end. Fantastic. So without further ado, we'll just start talking through some of the references. So FarmLab is what you see in front of you here. The modeling tools in FarmLab are, have been taken from the soil science domain. So the reference we'll give you today, and some of the techniques and processes can be found in the Soil Organic Carbon Mapping Cookbook, the second edition from the UNFAO. This is a fantastic resource when it comes to mapping carbon, but also just in general terms of digital soil mapping. This is a really great resource. I got a little diagram on the screen right here, which is one of the techniques that we'll be going through, which is a regression kriging technique. So key things are, we've got the boundaries, we've got the soil test results, and we have the depths. Important to also have access to the dates. Obviously, if we don't have the dates, again, it's very hard to know what you're modeling. So I'll just jump back in. We'll share my screen again. I'm pretty sure that, here we go. Fantastic. And now we'll jump into how to create some of these models. Now the way we'll be modeling today, and really importantly, is a combination of using some measured data and using some remotely sensed data. Why do we use both? The measured data gives us a good reference point on where to start, and the remotely sensed data is helping us do what's called interpolate that measured data across the landscape. So some of the remotely sensed data we'll be using today, what we call out-of-the-box data sets in FarmLab. So we'll have vegetation. This is vegetation here. This is one of our this is sort of one of our demo farms. It's cropped in the northern paddocks and grazed in the south, and there's a few interesting things that'll come out of that. We've got other environmental layers like elevation. Elevation is a really good one when it comes to mapping soil carbon and also understanding the variation of soil properties. This map here that you guys can hopefully see shows us that we've got relatively low elevation down south, up in the north of the farm up here, and then we've got a bit of a hill down south over here as well. Elevation by itself, there's some great scientific sort of literature that shows elevation itself is probably 70% or so correlated with soil organic carbon in particular. So it is a really nice starting point when it comes to creating some of these maps and models. But one of the other things to emphasize is we won't just use a single one of these layers. We're going to use multiple layers, and in what's called a multiple linear regression model using multiple covariates. And so we'll jump into that in a second. We've got some gamma radiometrics here as well. Great gamma data set for Australia, flown back in the mid-90s as part of the mining boom. We draw this from Geoscience Australia data sets, and it is a really fantastic data set for understanding the variation in soil type across the property. So, we come back to this one quite often. We have a lot of clients that will stratify by this initially, and then build their models with the support of this. Lastly, we also have some bulk density maps and clay maps from the Soil and Landscape Grid, as well as tree cover. Tree cover is a really nice one for biodiversity projects. We see a lot of clients now entering these biodiversity projects. You can use this to now exclude areas across the farm. We're not looking at measuring carbon. And I think one of the more exciting ones is topographical wetness index. This is exciting because, look, this shows water flow across the property. It's a really exciting metric because it does have a good correlation, slightly higher than elevation when it comes to measuring carbon in particular, but also nutrients and properties. We've found this is a really, really useful tool. So these are the layers. Please, if you've got any questions about the layers, chuck them in the Q&A. We can come back to these at the end of the webinar. And we'll go through how to use some of these layers, use some of these soil test results to create a map and a model. So first things first, we've got a series of boundaries here. Here are my paddock boundaries on screen. I'm actually going to use my cadastral boundaries to do the mapping and modeling, just because they're a bit more they're a bit more structured and accurate. And creating a model in FarmLab is relatively simple. So you've uploaded your soil test results. Again, there's a nice little template, nice little wizard you can use to import those. We can import those with the wizard there, download the template, and just throw those straight in. As long as it's got a geo reference, latitude, longitude, you're right. You're right. As I said, we also need the sample depth as well, and you want to have a date in there too. You know, some good data to model with. In our case, we're going to be we've got some soil test results here that were collected across the farm. There's quite a few we've got across this farm. We'll be using a series of these that have carbon against them to create a model. We'll see that in a second. So we'll go in, select our boundaries, and we'll select model. Wait for that to come up, and we can now select the dates that we want to model. I've got some soil test results from between January and February this year. We had this farm sampled, so we'll go into that and we'll scroll down and to see our carbon results there as well. So there's some carbon results. So I'll just pause here for a second and describe what we're seeing on the map. We've got about 2.84% carbon in the north part of the farm, to a high of about 5.19% at the southern end of the farm. Now this is pretty standard. We see this really commonly across a lot of our clients who have, cropped certain areas and graded certain areas. So surprise, surprise, the cropped areas in the north are relatively low in soil carbon, a percentage soil carbon at least, and the grazed areas in the south are relatively high. And we'll see that come through in the map once we've finished with the mapping process. Really, so this is pretty standard. I mean, you've got perennial pastures in the southern areas. You're maintaining that root growth, whereas these cropped areas do tend to mine the soil, quite a bit of soil carbon. Probably the other thing to mention here is we're mapping percentage carbon. In reality, what we'll do for a lot of clients, or what a lot of clients will do, is map the tons of carbon per hectare across the landscape. What's the difference? Well, percentage carbon is really just looking at the percentage carbon in whatever mass of soil was sampled. The tons of carbon per hectare will take into account the mass of soil, so bulk density. And that's usually done by testing for bulk density at the time the carbon test is done. Labs can do that. We work with labs here in Australia and the US to do bulk density testing, or we can calculate it under the Australian Clean Energy Regulator method requires a mass measurement by the lab, but a volume measurement in the field, and we'll use those calculations to determine the tons of carbon per hectare at each individual site. It really just depends, whether you model percentage carbon or tons of carbon per hectare. Look, guidance here is if you don't have tons of carbon per hectare, percentage carbon's fine. If you do, or you have the opportunity to get tons of carbon per hectare, please go out and record the bulk density and the mass, because it is a little bit more indicative of what's happening in the soil, because you're factoring into account the mass of the soil there as well, bulk density. And so we'll spend a bit of time mapping carbon today, and we'll have a look at the results. I will just talk briefly as we go through how to build these models, about the difference between how you might want to map nutrients, NPK, and how you might want to map carbon or clay sand silt. There's some ever so slight differences that you need to consider. Flipped onto the next screen here. So this is really where we set up the model itself. And so in this case, we pre-configure how to model. We pre-configure the name of the layer based on the depth you've selected and the dates you've selected there too. Nice and straightforward. We now have we now let you choose the method that you want to use. If you're new to modeling, I always recommend linear regression. It's the easiest to understand because modeling is quite hard to understand. So stick with linear regression. You can use some of the other regression techniques we have. These we just have as implemented the code in the back end to be able to run various different techniques for you. So you can choose, this is very much user driven here. So you will drive the technique you want to use. Random forest regression is also mentioned in the soil carbon mapping cookbook. And we do have some clients that have used it. It is a very good approach, gaining a lot of traction. The only challenge is it's very hard to interpret why you got that map. We'll talk about that later. We have the ability to create residuals. We'll talk about why this matters in a second. We'll just leave it on ordinary. And then you can select the layers that you want to use in conjunction with your soil test results to create that model. So this will bring together any of those layers I showed you earlier. We have all these layers for Australia. Globally, we have elevation and NDVI, and you can select the month and the year, and we're starting to incorporate more and more layers. So we're now looking at layers across New Zealand, the US and Canada, in addition to just elevation and NDVI as well. Very much user driven based on what our users want to do and how they want to map and model. So in this case, I'll just leave it as elevation NDVI. We'll actually, I can just hit start here and that'll go away and it'll start modeling. So that kicks off our servers and our back end. We'll go to one we've heard earlier though. This will take about 5 minutes to process. You should see that pop up relatively soon. So I'll just pause there for a second. We're going to go into our first model. Feel free to chuck any questions in the Q&A section, and we'll have a look at the results. So the layer we've got in front of us, we've got a model here. We've got 3 different models. This one I've run for bulk density. This one here I've run with NDVI and topographical awareness index. And the last one here I've run with elevation and NDVI. So 3 different models. If you look at them on the map, they look reasonably similar. They all show high levels of carbon down south, low levels up north in the cropping areas. We'll just go to the last one to confirm that. So first and foremost, that's a good thing. If you remember the soil test results, we had sort of 5% or so down south. We had sort of 2% up north. And because these maps and models are built using the original soil test results, we know we're getting a reasonably good answer there itself. Here we go. We've also had the last model there processed too, which is this one here, which is what we'll talk through today. So that's the again similar. We've got low levels of carbon in the north and high levels of carbon in the south. Fantastic. So we've got p-values and t-values, and we've got the metrics used. So the metrics used as we process them were elevation and NDVI, and they used the 9 soil samples we'd taken across the farm, about 152 hectares, about 320 odd acres, to build the model you see in front of you today. Now, some of you may be familiar with how linear regression works. Basically, we start with a cloud of sample points. We've got carbon. We might have carbon, percentage carbon down the bottom, and we might then have how that percentage carbon sample point relates to elevation and NDVI. And then linear regression simply draws a line of best fit through all of the cloud of points and how they relate to elevation and NDVI. All that means essentially is that we can look at any result. We can look at a result. We can look at one of these sample points anywhere, at any given location. We know that at this location, elevation is X and NDVI is Y, and we can then build a formula out of that. And we can predict using that formula what carbon looks like next to that point where we don't have a result. And that's really the fundamentals of how this works. It's a prediction across the landscape. So what you're looking at everywhere except for this point, actually including this point, is currently a prediction. But this really isn't enough. And it's not enough because the model has gone out independently and the model's been created, the formula's been created, but it's now independent of the sample points we've got. And so if we look at, where's a good example? If we have a look at some of these sample points here, the yellow number is about 2.53 to 2.69%. But if we look at the sample result here, we've got 1.86%. Who are you going to believe? You're going to believe the model that's just been generated, or are you going to believe the actual test result? Most of the time, you should be believing the soil test result. There's a little hint, and the reason for that is it's tested. That's the accurate thing. That's the accurate result for that location in the paddock. Pretty common sense. So the challenge here is, how do we now incorporate the accurate results with the model that's kind of independent, stands alone? And this is that step in that flow diagram I quickly showed you earlier from the FAO Soil Carbon Mapping Cookbook, which is creating the residuals. So residuals are basically the distance from the model that each of these soil test results sit. So if I just zoom back in there for a second, we can have a look at a map of the residuals, and I'll explain what I mean by that, because it is a little bit tricky to get your head around. So basically, when you have a red streak and line across this, the model is over predicting to what the soil test is. So the soil test result is lower than the model. Where you have blue, the soil test result is higher than what the model is predicting. And so you can see quite clearly in this that we've kind of very much over predicted here. The soil test results are showing much lower than what the model is showing. And in the blue area, the soil test results are much higher than what the model is predicting as well. And so what we want to do is we basically want to take that first map here, and we want to take this map, and we want to smush them together. And we get this map here. And so this is a more informed map. This is really essentially the final product that we recommend our users use here, because this has both the model that's just been run. Now, if it's an accurate model, and we'll come back to the R-squareds and the accuracy in a second, it may be good to start with, but we always really want to reincorporate the actual soil test data, the actual ground truth data against the farm there. It's a really sort of essential step. In other methods like random forest, you won't have to do this. It will factor into account, kind of do this automatically for the sites you've taken samples from. But really, in any linear regression modeling technique, you want to reincorporate the soil test results to ensure that you have an accurate final product. And so this is very much the final product. And we'll just talk through this before we go back and sort of talk about some of the stats here. We've got blue, so that this is slightly changed from what we saw here. It's a bit, brings it in a little bit more, we like to say. So we got high carbon up here. This is sort of the graze country. Also around about the native vegetation, native levels up down south in this property. We've got a paddock here that's been extensively cropped and tilled. I know because I think we may even have in the satellite imagery. Is it fallow? No, I think there might be a slight crop growing there, but I know that's been left fallow for some period of time, which has probably influenced carbon. And then we have slightly higher levels, sort of even further down south, and that's probably driven by some of the better soils down the very northern end, I should say, of the property. This is closer to the creek, where it gets a little bit lower in elevation. So that sort of describes what we're seeing here. We'll just come back to some of the stats. So we had the P&T values here. We'll indicate how closely a fit each of these variables has with the model. So elevation in this case has a p-value of 0.01 and a t-value of 3.15. Now, I'm going to try and explain this. I'm more than happy to be corrected in the comments here, but basically there is a 0.01% probability, or a 1% probability that this result will lie within outside of 3.1 standard deviations from the mean of the model that's been created. So it just means that terrain is an accurate indicator of soil carbon in this case. NDVI, vegetation, not so much. There's a higher probability that the NDVI will predict within 1.35 standard deviations of the mean. So it's probably not a great fit for NDVI. Now we've if you look closely here, you can see we've actually color coded the answers here for you. So if something's in red, it's probably not superbly accurate. But the key thing you should always be looking at first is the R-squared. So the R-squared here is 0.75, 0.76, with a root mean square error of 0.66. That R-squared is not too bad. That's pretty good for an environmental map, to be honest. And that means once we've created the residuals, you know, again, that map gets even more accurate because we've reincorporated the actual soil test results, so it's no longer just the model by itself. So this is something that we would absolutely recommend our clients trust. Now, if you saw earlier, we actually built 3 of these models using various different layers to show the difference in sort of models. And we can build one of those, which was bulk density, actually had a much higher R-squared than this. And that's a great thing. So we would certainly recommend that when you're modeling, you run multiple models. We don't always know what's going to work in what regions. Sometimes, in this case, bulk density works better than these 2 layers, but in other areas, we find just the opposite. We might find K-gamma and topographical wetness index have the best correlation with soil carbon. This is one of the magic things about soils and soil carbon in particular, is that it really is horses for courses. You go to a different region with different soil types, you're going to find variation in how to build these models most accurately. So you know, so just something to bear in mind. You do have the tools at your fingertips to create these models according to your region, and we do work with users, and we do work with you know, with our clients to ensure that they, you know, can build up some expertise and some IP in their region around what works. We find this with stratification. There's another, there's a few other resources on stratification and how to stratify, but I certainly find with stratification that is the case. That brings me to the end of my very in-depth statistical discussion about models and how to model in FarmLab. The last thing we'll say, which is these models can then be used for stratification. And actually, that's probably a good point, is when these models are used and why they're used as well. So we have 2 main use cases for these models. The first is management. So a client might look at this as a carbon map, and then may want to identify the areas to improve. So a really important thing here when it comes to understanding what's been done, where on the farm might be, they might need to focus more on, you know, improving ground cover and other things that relate to improving soil carbon, and other areas of the farm that, you know, maybe, you know, may mean that may give them better insights into what their historic management practices over those areas were. So we have a lot of clients that are sort of surprised by these and go, well, I didn't realize I had such high carbon over the, you know, that part of my farm. That's the part of my farm I've had a mixed species pasture or something in, or I've had you know, or I've got low levels of carbon and I've been doing this. And it helps correlate the management practice to the change in what they're seeing in the soils. The second thing is these maps can be used for further sampling and stratification. And so we can go in, and I can go in now that I've created this map, and I can select my boundaries again, and I can re-stratify by that carbon map. So there's the carbon map with Krieg residuals there. Now I can take that and I can stratify that. Why might I do that? Well, in the Australian context, for clean energy regulator projects, clients get discounted for any variance that they have in their measurements of carbon across their strata. So if you're starting with a carbon map to start with, even based on a few soil test results, you can drastically reduce that variance. We've found a reduction in variance by 3 to 5 times by just using some of these pre-baselining, using some of these maps to inform that. Now, the very last thing, almost got to touch on it, is nutrients versus properties. So we've gone through today, we've created lots of maps for carbon, spoken about the stats. How can we use this to create maps for nitrogen, potassium, phosphorus? The answer is yes, but depends on the parameters. So when you're sampling and when you're creating these models and maps for nutrients, you just need to be aware that nutrients are very heavily driven by management. What do I mean by that? Well, if I measure carbon in the southern part of this cropping area, I've had, you know, I've had some, you know, something nitrogen fixing in this, and then I measure nitrogen in the sort of northern paddock up here and I've just had wheat or barley, I'm going to see drastically different levels of nitrogen. Those will be measured, but importantly, when it comes to generating these models, I'm using these covariates here. The covariates may be exactly the same. And so factoring into account the management history of the paddocks is a really vital piece of mapping nutrients. In our case, we would only recommend, we would just recommend you still absolutely model for nitrogen, potassium, phosphorus, but do it on a paddock by paddock basis. And that way there's no variance in management across the farm scale model that you've got. So try and really do it at the paddock scale. So collect maybe 3 samples across this paddock, build a nitrogen map for this paddock. Collect 3 samples across this paddock, build a nitrogen map for this paddock. But don't try and build the nitrogen map across both paddocks there, because you'll see there'll be too much unknown variance driven by that historic management practice change. With properties, carbon is driven by management practice change, and we've seen that across this farm here. However, we find that we've got these landscape scale, particularly elevation, topographic wetness index, bulk density, these landscape scale covariates that often explain more of the change in soil carbon than just the management practice alone. So it's not as driven by management, but it is driven by management. And there are other techniques that we would suggest. So if you've got a mixed cattle cropping operation, we would suggest you build, as I said, as I described the nitrogen before, separate out your models, do a model for your crop and particularly crop type, and do a model for your grazed area there as well. It will just work better that way. All right, well, that brings us to the very end of the webinar, and I just want to say thank you for joining me. So, look, if we've got any questions, please fire away. More than happy to answer any questions you've got. This will be recorded, so we'll probably stop the recording just after the questions. If you'd like to see this again, we'll be putting this on the website in the next 2 to 3 days as well. Will there be any capacity to model to 1 meter? I noticed the standard setting was 30 centimeters. Depends how deep you measure. So this is a really good question. What we see is if you were to take a measurement, if you take a core sample at any site and a series of sites across the landscape, and you had one result for 0 to 1 meter, you could model that, absolutely. It would show you the change in carbon at 0 to 1 meter. However, if you have 0 to 30 centimeters and 30 to 1 meter, you could model each independently. We have now just disabled the ability to model 2 depths together. Now, the reason we've done that is more as a fail-safe for our users, because soil does change at depth. If you have 2 separate horizons of soil, we want to avoid you modeling them both and getting something that's probably not entirely accurate. This is mainly for NPK, soil properties as well, but also carbon. So I guess the short answer there, Dylan, is if you've sampled to 1 meter and you have one result from 0 to 1 meter, absolutely, we can model that across the landscape. If you haven't, then do it at each individual depth. Great question. Actually, probably something to add to that, and feel free to throw more questions in the chat or in the Q&A section. If you have gamma is probably has the best correlation with what's going on underneath the surface, and that's partly because these gamma surveys that were run or flown, they measure the breakdown of soil parent material. It releases a gamma ray in various different spectrums. The ones we measure are potassium, thorium, and uranium, and that's often happening under the surface. So it's a good it helps us. It usually has a good correlation with what's happening between 30 and 45 centimeters under the ground. But some of these other factors like NDVI, topographic wetness index, and elevation usually help us correlate well with sort of the top 30 centimeters. To create a registered project, who defines the sample locations and how many samples per hectare? Great question, Stephen. So for a registered project, the sample locations are determined randomly. So we actually have a tool. I'll show you that right now. We have a tool here. So you can stratify in FarmLab, and then very easily you can go and you can turn your strata into boundaries here, and then you can generate point locations. Now this will generate the number of points. We'll talk about that in a second. You plug in there using a seed number. That seed number is usually determined by some unknown date in the future. And again, we give you some guidance on how to do that for an Australian Clean Energy Regulator project. Read between the lines. We normally just say, take the date timestamp of the response email from the regulator and plug that into there to be your seed number, because they might respond to you at any time, so you can't predict it. So importantly, it's just a way to not allow you to predetermine the sample sites until the regulator have approved your strata plan. Now, the number of points is a really good question. This will vary. It will vary according to the size of the farm, the variation of soil, the budget of the client as well. We usually say, once your strata are accurate, hand on heart, you've taken that strata map to your clients, and they believe that's an accurate reflection of the variability of soil carbon across your farm. Usually between 5 and 10 samples per strata is a good starting point. Now, if the strata are, that's assuming the strata are between 50 and 500 hectares each. If they're probably 50 and 300 hectares each. If they're bigger than 300 hectares, each individual strata, you probably want to have more carbon, just because there's going to, even if you use one of these carbon maps, there's probably still more unexplained variance within each of those strata, each of those zones that you just can't describe. And so having more samples is a way to cater to that variance. So really good question there. Fantastic. If there's any more questions, chuck them in the chat. Otherwise, we'll get it wrapped up. Just want to say a big thank you. As I said, we'll put the recording on the website in the next few days. And if you have any more questions, please don't hesitate to reach out to us. I'm Sam. Email address is sam@farmlab.com.au, or one of our team. Yeah, so have a great day. Thank you very much.